Come on in, everyone. Come on, come on. Sorry, my computer took a long time to connect. I don't know why, but we are now finally getting students coming in, and I am now available. Feel free to ask me questions while we're waiting for the rest of the students to log in. Looks like I got 13 of you so far, 14 of you now. So anybody have any questions while we're waiting for everybody? All right, we got 14 people. I guess that's enough to get started. So, if I remember correctly, your homework was either due last night or it's due tonight. I can't remember if that was for chapter one. Hopefully, you all got that knocked out. In general, our homeworks are always supposed to be due on the Sunday. So just get more used to the Sunday because it's not going to be normal for you to have that, Monday to turn it in or Tuesday to turn it in, that kind of thing. So just remember 11:59 p.m. every Sunday, you should probably have two assignments or even more due. There's also occasionally extra credits that you can turn in. You'll see the due dates on there. So you can turn those in. This one I recommend you do it. When I give you a extra credit, it almost always is supposed to benefit you within that chapter. So I try to make it due the same week. That don't mean I necessarily won't give you credit if you do it a little late. It just you doing it late allows you to do it, but it doesn't help you understand the chapter better, which was the whole purpose of it. Except for some of them, like the extra credit where I asked you to divide 1 by 243. That's just an interesting problem and uh, that kind of thing. But other than that, most of the time the extra credits are very related to what we're doing. So if there is no questions from anyone, I'm going to move along. And it looks like it did not allow me to connect to my lab and mastering for some reason. But that's okay. I am going to now go to my lab and mastering. Week two will be available or should be available already. Let me double check while I'm on that in modules. I've got week one is definitely available. You see a ton of stuff in there. Week two was not made available yet. Okay, if you look now in Canvas, you will see that in fact, week two has been published. Conceptual questions and homework questions are there. Uh, the lab that I listed is not the actual lab, so I'm turning that off right now. We will do this lab later, but that's just not what we're doing right now. Okay, we got that. Propagation of error, that's gonna be gone. Okay. All right, so now that's set up. So what I'm saying here is we're gonna go ahead and start into chapter two, which is where the actual quote unquote physics comes in. Chapter one was largely just making sure you know how to convert units and that you knew about scientific notation, that you understand the process of science, how that goes along, and that you know keywords like law, theory, hypothesis, stuff like that. Uh, there's also some quick back of the envelope type computations you should be able to do that we call them Fermi calculations or estimates and stuff like that. So hopefully you've got all that knocked out. Uh, we are now starting chapter two, and chapter two is actually, and this is the whole reason that I had tried to open the text. Chapter two is called describing motion, kinematics in one dimension. So, what we're doing there is we're actually studying motion without respect to what causes it. So, if I were to tell you that a certain object has a certain acceleration and give you that as a function of time, uh, or if I said that it has this acceleration and has certain values of velocity and or position at two different times, then in most instances, you can actually then derive an equation for the velocity as a function of time and another one for the position as a function of time, as long as you have those two initial conditions. And that's sort of what we're shooting for in this chapter is we're going to actually figure out how to make those equations. And that type of thing where you're studying motion without necessarily understanding what made it have that acceleration as a function of time or that velocity as a function of time or that position as a function of time, we study that motion without respect to that. And when we're doing so, we're studying kinematics. Once we bring in the idea of F equals ma, which allows us to determine what the acceleration is if we know what the forces are, then we're doing dynamics. And kinematics and dynamics together make what we call uh, uh, mechanics. Okay. So hopefully that helps you. Sorry, I was doing like three things at once, so I had to have a lot of ums in my question, in my statements, because I was trying to do too many things at once. Uh, yes, for the conceptual questions, it's supposed to take the highest score unless you did one after the due date, and then I think it might actually take the score there with the penalties. So you don't want to mess with them after the due date, except if it gives you practice ones, you're allowed to do those. Or if it's set that you can do it later for practice, that would be okay. But I don't think I set it for practice on any of those. So it's just I leave it available so you can go back and look and make sure you understand how you did those problems. Yeah. So that was answering Michael's question. Anybody else have a question? All right. So what I'm going to do now is I've got my ebook open, but I've got it open to like chapter 18, which we're doing in 242. I am going to now open that in 241 and tell you that basically in the study of physics, you in some sense need a coordinate system. You don't, the laws of physics are true no matter what the coordinate systems are. That's the general theory of relativity. The laws of physics are the same for all uh, systems and are for all reference frames, period. No ifs, ands, or buts about it. That is general relativity. That's a part of it. So we can make our coordinates any way we want. But the important thing is sometimes it is important to actually have coordinates chosen. And then there's tricks that you can use where if you choose coordinates wisely, then that's a smart thing. For instance, you could have, four forces, one at 45 degree this way, one at 45 degree this way, one at 45 degree this way, and one at 45 degree this way. If you just blindly plugged in a coordinate system where the x-axis points to the right in the positive direction and the y-axis in the positive direction points up, you could use that coordinate system, but if you're trying to add those vectors, you'd be crazy to do it because why not put the vectors right along the axis? So if you tilted your coordinate system where your x-axis was parallel or anti-parallel to that first one and that third one, and your x and y or your y-axis is parallel or anti-parallel to that second and fourth one, that's a way you could use a coordinate system to help you. So there's a lot of neat things you can learn about coordinate systems and how to choose them so that your problems are easier to solve. And that's sort of what we're getting at with section 2-1, which is just reference frames. So read over that section and that'll give you some sense of how it works. And also towards the end, let me double check. No, that's basically it. I was thinking, in fact, this might be in chapter 3. There's a related relationship between velocities, relative velocity, and stuff like that. Yeah, I just double checked. That is chapter 3, so I don't have to worry about that. But the reference frame is something relevant, and you're going to see me use that today to some extent. But in order to do so, we need to define some parameters and then go through those parameters and work out the details. So your book talks about drawing an x-axis and a y-axis, and there should be perpendicular to each other. That makes them Cartesian coordinates. That doesn't mean you can't use a non-Cartesian coordinate system. You certainly can, but a lot of things get complicated when you use a different coordinate system. So if you use the x-axis that was pointing to the right and horizontal, but you could in principle choose a y-axis that's maybe 60 degrees rotated from the x-axis. That coordinate system works, but if you use formulas that you're used to using, like for cross products and dot products and vectors, a lot of those formulas aren't going to work in that new coordinate system. You got to do some work. So it's best usually to stick to Cartesian coordinates until you actually have a really good reason for using like polar coordinates, cylindrical coordinates, spherical coordinates. And those really don't come into play until basically we get into chapter 21. You could have used them back in chapter 6 when we did gravity, but again, that's neither here nor there. So the first thing I want to define for you guys is a concept called displacement. So there's a concept called distance and there's a concept called displacement, and they are related, but they're different. What you'll find out is displacement is what we call a vector quantity, and distance is a scalar quantity. So you might, for instance, consider a coordinate system. Now let's draw a coordinate system. Let's say this is going to be our coordinate system right here. This right here is going to be your x-axis. And this right here would be your y-axis. And you might imagine that you walked starting in here. So this spot right here is x0, which is called your initial position.
Hey, Professor.
Yes. Oh, I should share the screen with you, maybe. Yes. Thank you. Sorry about that, guys. Literally just jumped right in and forgot to share it. So that won't help you very much. All right. Sorry about that. Thanks for reminding me. All right, so what I've drawn here is an x-axis and a y-axis, and I've specified that little green circle there at the middle is supposed to be my initial position, and we would call that x0. In fact, in 3 dimensions, we would call it x0 or R0 with a vector symbol over it. We're not studying vectors yet, so don't worry about that. I'm just telling you that's where it's coming from. So now what we do is we imagine we walk, let's say 100 meters. So I'm going to say this would be 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that's pretty close. Actually, what I'm going to do is make it a little longer since that's 18. I'm going to go ahead and extend this to here. Whoa. I'm going to do it with red. Okay. And now that's 18, 19, and 20. So if we count each 2 blocks as 10 meters, then this guy right here be 20, this guy be 30, 40, 50, 60, 70, 80, 90, and 100. And this, of course, is all drawn in meters, say. Okay. So what we might imagine is we walk a full distance of 100 meters. Whoa. I need to go green again. So I'm going to walk all the way to 100 meters, and then I'm going to walk back 30 meters. And that's where I'm ultimately going to be. So this would be called X. In 3D, that would be X bar or X arrow R arrow, the position. Okay. So notice this one right here was 30 meters. This trek right here had a distance of 100 meters. So the distance traveled is equal to 100 plus 30, 130 meters. The displacement, however, is delta x, and that's going to be x minus x0, which you can recognize as 70. That's where that dot's supposed to be. I didn't draw it very well. In fact, let me fix that since I'm trying to be somewhat precise here. Okay, so that's that. Okay, now y'all see that dot is in fact on the 70. So we'll now do 70.0 meters minus 0.0 meters, which equals 70.0 meters. So your displacement is, in some sense, is like a vector. It's a vector that points from the initial spot you were in to the final spot. Displacement is a vector. Again, we're not learning about those yet, but I'm just showing you in advance a little bit about what we're going to. Displacement is a vector that is found by drawing a vector, which we can just say an arrow, because that's a really good representation of a vector, is an arrow. So drawing a vector from the origin of our coordinates whoa, went bad there. Don't know what happened, but anyways, dang it, everything looks bad. I gotta make that a little better. From the origin of our coordinates to the initial position, and then someone else try to come in. A vector from the origin to the final position, and finally subtracting the initial position vector from, make sure you realize that, from the final position vector. Okay, so notice the initial position vector is really just zero vector. So above x0 is just a zero vector. Okay, because it's supposed to point from the origin to where the thing was initially. The thing is at the origin, so you don't need to move at all. The distance, which is from the origin to it, is zero. So the vector is zero, and the final vector position X is in fact pointing from is 70.0 meters from origin to, let's actually reword that. Let's say to the point X. So if I wanted to actually draw a vector, what I could do is I could say my initial vector x0 is equal to the 0 vector. So it's just a dot there. But my final vector is that vector right there. Okay. So right now, as far as vectors are concerned, all you're thinking of them as little arrows. But the main thing is what I want you to see is displacement is entirely different from distance. In this case, for instance, you can imagine walking, let's say, from the middle of your house, say, lined up on the road. So you line up your center of your house with the road, you step onto the road and you look back, and then you take a walk that one way down the road, let's say north, and you go for 100 meters, and then you stop, turn around and walk back another 30 meters to the south, and then you stop. So the displacement in that case is 70 meters pointing to the north direction, and the actual distance traveled was 130 meters because that's the total distance you walk. Does that make sense to everyone? So the key words here are distance and displacement. Okay. So everybody understands the difference between distance and displacement on that? Anybody have any questions? Thanks, Jude. All right. So now that we have that, we can start doing things like, let's say, what is the average speed? Or what is speed and what is velocity? So we'll start off with average speed. Now, hopefully you already know a formula for this, and you should be able to figure out one even if you don't. All you have to do is think about what are the units on your speedometer. So average speed is what we'll attack first. Which is often given the symbol S with a bar over it, and the bar means average. Okay. Now, I said all you have to do is think about the units on your speedometer. So can anybody tell me what the units on the speedometer of their car is?
Miles per hour.
Yes, miles per hour. Can anybody tell me specifically what the unit of a mile is? That's measuring what? Is that measuring time? Is it measuring
Length.
very good length? Or distance is another way of saying it. That's fine. And the hour measures
Time.
time. And per, do you know mathematically what per often means?
Divide.
Divide, exactly. So what I'm going to tell you is that the average speed, not using length like you said, I'm going to go ahead and use distance, but you see that you were right anyways. That's the main thing. So what I'm going to do is I'm going to take the distance traveled and since the speedometer said it was distance divided by time, then I'm going to divide that by the time taken. So if the walk above took, let's say, I don't think that's a very good number. I'm going to say, let's say it took 7 seconds. That's actually really, really fast, but that's okay. What that would mean, though, is in this case, you'd get 130 meters divided by 7.0 seconds. And of course, that is, I'll actually just use my calculator rather than try to give you a neat way to work it out. 130 divided by 7 is 18.5. Whoa, no. Meters per second. So that's what your average speed is. Every time someone asks you to calculate your average speed, you're just going to take distance and divide it by time. You'll learn later that if you're dealing with a constant acceleration, then there's another formula you can use. But right now, we don't care about that too much. So that's what speed is. Speed is a measure of, or more specifically, you can call it a rate of change of distance. Okay. And there's another side to that that actually includes not only how fast you're going, but in which direction. And that is something we call velocity. So velocity is a vector quantity again. Notice it starts with a V, as does vector. And its average is the change in displacement remember displacement, not distance, divided by the time taken. So for instance, in our case, V bar is equal to delta X over delta T, which this delta, that Greek letter there, looks like an upright triangle. That is called delta. It's the third letter. That's actually a capital, by the way. It's the third letter of the Greek alphabet, alpha, beta, no, excuse me, alpha, beta, gamma, delta. It's the fourth letter of the Greek alphabet. And it always means final minus initial. So what you're supposed to do is whatever symbol comes next, for instance, in this case, it's the X, you're supposed to take the final X and subtract from it the initial X. So in this case, it's going to become X minus X0 over, and you could just say T minus T0, but we almost always start the timer at the beginning. So T0 is equal to 0, but that would be your displacement. So since it's a displacement, what we get for this example V bar, or excuse me, I actually could write V vector with a bar over it as well. I'm going to go ahead and erase that vector symbol because we're not really studying vectors so much right now. So I don't want to make it more complicated than it needs to be. But I do like you knowing where we're going, but I'll just put the bar over it. Now, in this case, what we discovered is the displacement was just 70 meters. So we did 70.0 meters divided by 7.0 seconds. And that gives you, of course, 10.0 meters per second. That is what the average velocity would be. But since we're talking about velocity, technically we'd say 70 meters per second north. Okay, that would give you the other part of the quantity that you have to have, because the bad guy in the original Despicable Me was named Vector, and he said it's a mathematical term that means something that has magnitude and direction. And he said he's Vector because he does evil with direction and magnitude. Okay, so literally the only step that goes beyond this 10 meters per second is say due north. Okay, so v, the vector, is equal to 10.0 meters per second due north. And now you can see by including the word due north, I can actually put the vector symbol on top. Right now, we're just dealing with one dimension. So the vectorness just turns out to be the magnitude, and then the positive or minus is the direction. In one dimension, the magnitude is found like done, immediately above, and the direction is given by the sign. And by that, I mean positive / negative. So our coordinate system, evidently, based on the words I said, had the x-axis pointing in the positive direction to the north and the negative direction to the south. So just by saying positive 10.0 meters per second, I've actually covered the vectorness of it. Okay. Now, if you had a coordinate system like this one, let's say, notice I'm going to switch coordinates here. You'll see in a second it's slightly different than the coordinate system I drew earlier. Specifically, I'm going to put over here, I'm going to put the time axis in seconds. And up here, I'm going to put the x-axis in meters. And let's say after 1 second, you had gone a distance of 1 meter. So this is 1, 2, 3, 4, 5, 6, 7, like that. And let's say after 2 seconds, you had gone 2 meters. And after 3 seconds, you had gone 3 meters. And after 4 seconds, you had gone 4 meters, like that. Okay. Now you can actually draw a line of best fit right there. Oops. I changed the red, but it didn't change the red. So the line of best fit is that right there. And when you look at that graph, you can say, oh, well, all these dots seem to be lying perfectly along this line. I should maybe make them a little bigger just to make that obvious. Okay, so they hit like that. Now, the neat thing is, if you look at that, it seems that this is pretty consistent motion. Like I only gave you the first 4 pieces of data, the 1 second, the 2 second, the 3 second, and 4 second distances. Anybody want to take a guess what the 5th second should be at? So
5
this
meters.
is sort of your hypothesis. Go ahead. What do you think it was?
5 meters.
Exactly. So yeah, that's what I'm going to do is I'm going to draw this dot right here, and just assuming that the motion is going to continue as it is, we were able to make a hypothesis, and that hypothesis fell right on the curve. So that's kind of nice. But we could also figure out something else. What if, for instance, we had some different data, and let's say this data is going to be graphed by blues. So let's say we have a blue dot for 1 meter at 1 second, but then at 2 seconds we go 4 meters, and then at 3 seconds we go all the way up to 9 meters, which would be right here. So in this case, you see the motion's not uniform. You could probably still make a hypothesis about what the 4th second would be, but you really need a few more points to make sure. So how do I calculate the velocity in this case? Well, if we look at the original red line, what is the slope of this line? So what is the slope of the red line? Anybody?
Just one.
Just one. Very good. That's exactly right. Now, let's take it a little step further. You did say one, but remember we calculate slope by doing rise over run. So we might be able to go like this, say, and then back to here. This is our rise. And our rise is obviously 5 minus 2 over, and then our run is 1, 2, 3, which is 5 minus 2 as well. And from that, you get 1.0. Now, you're exactly right. That's exactly what the slope is. Now, with that in mind, can you tell me what the units of the slope should be?
Meters per second.
Exactly, because this was 5 meters minus 2 meters over 5 seconds minus 2 seconds, which gives us 1.0 meters per second. Isn't that the same as the units for speed or velocity?
Yes.
Yep. So that's the trick here is we realize that, oh, on a position versus time graph, the slope is the velocity. So on a x versus t graph, the slope seems to be like the speed or velocity. What I mean by speed or velocity, well, when I found it was 1 meter per second, I knew that that's consistent with the speed. However, when I found it was positive 1 meter per second, then I realized, wait a second, that positive's telling me it's moving in the increasing coordinate direction, so it gives me the direction as well. So it is like the vector quantity. If I compare the red line, any two spots on that red line is still going to have the same slope. All those have exactly the same slope. So the slope is a constant. And lo and behold, that means speed and velocity are constant. Okay. That was really bad the way I did that. So let me spread it out a little further. Speed and velocity So that's our big eureka moment, if you will. Now, if you wanted to calculate the velocity at any point, let's say on the blue curve as opposed to the red curve, then you might want to say, let's consider this point and this point and draw a line from there, and that would give you in some sense an average velocity. But if we let that second point get closer and closer and closer, what happens is, I'm going to blow it up here. So I have a red line, a line like this. This is called a secant line. You don't really necessarily need to know that for a physics class, but that is what they call it in mathematics. But if you allow the elapsed time to get smaller and smaller, you approach the instantaneous velocity. So if we allow the time interval to get a little smaller, it might go from here to here. Or smaller still, it might go from here to here. And smaller still, it might go from here to here. Eventually, if you let the time get infinitely small, then what you'll discover is you have a tangent line okay, as delta t approaches 0. So by doing that, basically, eventually what's happening is you're saying, what's the average speed between 1 second and 2 seconds? So you could treat that first dot as 1.0 seconds and the second dot as 2.0 seconds. And of course, a second is a amount of time that humans are pretty good at dealing with. So we might actually be able to sense that we changed in our speed from the first second to the second second. And therefore, we wouldn't necessarily be satisfied if I was trying to find out my instantaneous velocity. I wouldn't be satisfied by calculating the average over that whole second. But if I cut it down to half a second, then I probably would not sense quite as detailed or I wouldn't get as good a sense of how much the speed changed from 1 second to 1.5 seconds. So that's getting closer to something I'd feel comfortable calling an instantaneous velocity. But if I continue to get smaller and smaller, eventually I'd get maybe to a tenth of a second. And humans are not very good at detecting much of a difference in tenths of a second, except for stuff like your brain calculating the difference in time between a signal arriving at its right ear and its left ear and stuff like that. Other than that, we can't really discern what a difference in time of about a tenth of a second is. So that time interval might be close enough to pretend like it's 0. All that really matters is when I calculate that, and then I calculate it again for 1/10 of a second, and I calculate it again for a different tenth of a second. If I consistently get roughly the same number to the number of places that I can round it to, then I'd say that that small interval is small enough. In principle, what you're doing is you're letting the time interval go to 0. So ultimately, we discovered that the average velocity is delta x over delta t, but the instantaneous velocity is equal to v, and that is the limit as delta t approaches 0 of delta x over delta t. And I think that I just, tipped my hand and showed you that dx dt is in fact equal to, take off that vector symbol, v that way. Does that make sense to everyone?
Yeah.
We also have, by the way, the average speed is just distance divided by time. So these are your basic equations that we found so far. And in fact, we can do it one further. We could actually make a graph again like I just did, but this time instead of making a graph of position versus time, I could make it a graph of time in seconds and velocity in meters per second. And in fact, if I had a similar scenario where at 1 second, I had a velocity of 1. At 2 seconds, I had a velocity of 2. At 3 seconds, whoa, no, that's supposed to be here. Sorry about that. At 3 seconds, I had a velocity of 3, so on and so forth. When we do that, we can see that this is velocity as a function of time. It's a linear expression. And in fact, what you can figure out is if you take any two dots, you will see that the slope is a constant. So again, we have slope is a constant. So can someone calculate that slope?
Wouldn't it be 1 meter per second per second?
Yes, you'd say 1.0 meters per second divided by 1.0 seconds, which is 1.0 meters per second every second. Okay. Now, this is the definition of constant velocity. So that whole concept of velocity was essentially invented by, or discovered, if you will, by Galileo. So Galileo, after facing the Inquisition, where they were going to take away, they were going to basically cut his entrails out and show them through them and stuff like that. He recanted and had to take an in-house arrest. And from there, he was forbidden to talk about astronomy and stuff like that. But by then, he had realized that in order to make sense of the universe, he needed to make sense of motion. So he started to study falling bodies, but they fell so quickly he couldn't tell anything about it. But what he discovered was, proportionately speaking, you could actually slide or roll things down inclines, and the ratio of the height to the horizontal distance could be related to a ratio of the acceleration due to gravity. So from that, he could make some sense about motion just by studying how motions behaves going up and down inclines. And what he did was introduce the idea of speed, which is the distance traveled per time. And then ultimately, when we get to vectors, which was after Newton, vector calculus was basically invented in the 1840s to 60s, somewhere in there. It's partly by Oliver Heaviside and partly by Gibbs of America. But either way, once you get into that, that's a slightly different story. But the main thing is Galileo came up with the idea that constant velocity is a velocity for which during a given time interval, you always change your speed by the same amount. So when you say velocity of 1 meter per second, that's suggesting that your velocity is always going to change by 1 meter per second each second. That's the very definition of constant acceleration. The very definition of constant, oh, I said backwards, no wonder. I just evidently said that and was thinking to myself, did I make a mistake? And evidently I did, because I wrote it right there. But as constant acceleration. And this graph right here, slope is a constant, is definition of constant velocity. So if during a given interval, in this case, 1 second, if you always cover a distance of 1 meter in 1 second, then you have a constant velocity. If you always cover the same change in velocity in a given time interval, then you have constant acceleration. So let's say 3.5 meters per second is a constant, well, velocity if during any 1.0 second interval the position has changed by 3.5 meters. Okay. That also means in delta t equals 0.1, then every change in position will be 0.35 meters. Or if you did half a second, it'd be 1.75 meters, so on and so forth. So that's the definition of constant velocity that Galileo got from us. And now, let's say 4.0 meters per second every second is a constant acceleration. If during any 1.0 second interval, the velocity changes by 4.0 meters per second. Okay. So you can see basically what we're talking about here is the fact that any 2 points have the same slope right here. So a graph of velocity versus time, if it's a straight line, that is constant acceleration. If it's a horizontal line, it would be constant zero acceleration. If it's a positive slope line, it would be positive acceleration. And if it's a negative slope line, it would be negative acceleration. And in fact, it doesn't necessarily have to be a constant acceleration. In fact, we could add some more dots. And I could say, let's say at 1 second, it was moving at 1/2 of a meter per second. And then at 2 seconds, it was moving at 2 meters per second. And then at 3 seconds, it was moving at this speed, which is 3, 4, 5, 6, 7, like that. Then our line of best fit might look more like this. Okay. So again, you could do the same thing and say A bar is delta V over delta T. and A instantaneous is equal to the limit of delta V over delta T as delta T approaches 0, which is dV dt. All right. So does anybody know a particular figure that, let's say, a car salesman might give you that is exactly consistent with telling you how much acceleration the vehicle has? There's a lot of numbers that you could come up with, but to be honest with you, there's only one that gives you exactly the acceleration. Can anybody tell me what that is? If you don't, yeah, that's what I'm looking for, Alex. Anybody else? In case y'all didn't see that, I want to give everybody the opportunity to think about it. So a lot of people will say things like torque or horsepower, stuff like that, rear end gear ratio, all sorts of stuff like that. And all those have an impact on exactly how much acceleration a vehicle can have. But if you actually go to try to determine the acceleration, one test you could use is say, let's see how long a vehicle takes to go from 0 miles per hour to 60 miles per hour. And a typical number that used to be good back before Tesla came along was 0 to 60 in 4 seconds. So that would be, you know, a right off the line Camaro or Mustang, right off the line, not the special GTs or any of those type things. Those are even faster. But 0 to 60 is a direct measurement of acceleration. In fact, acceleration is supposed to be the change in velocity divided by the time taken to change that velocity. So in this case, it'd be 60 miles per hour minus 0 miles per hour divided by 4.0 seconds. That's 60 miles per hour divided by 4 seconds. That's 15 miles per hour per second. That is the measure of acceleration for that, 15 miles per hour per second. That is a very good measurement. So let's say I'm going to write it here. I'm going to write it in black. 0 to 60 miles per hour in 4.0 seconds implies the average acceleration is 60 miles per hour minus 0 miles per hour divided by 4.0 seconds. And I'll actually assume that these are measured to at least the 10th place. And this becomes 60.0 miles per hour over 4.0 seconds. So you could actually call this 15.0 miles per hour per second. And if you made a plot of velocity versus time for this, then this time in seconds would be, let's say that's one, let's say, actually, let's do, yeah, I think 3 can do it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 4.0 seconds, 3.0, 2.0, 1.0. And this would be velocity in miles per hour. And if this were indeed constant acceleration, you would expect let me say this is going to be 15. This is going to be 30. This is going to be 45. And let me expand a little bit further on this. I need to make that graph just slightly larger than it is. And this is V in meters per second is the axis, so I'll just label it that way. So what this is actually showing us is that if I made a plot of these, I would expect the car to reach 60 miles per hour after 4 seconds. It's going to meet 45 miles per hour after 3 seconds. It'll be 30 after 2, and it'll be 15 after 1 second, and it'd be 0 at 0 seconds. So you'd expect the line to look like this. Now, in principle, that's really not a reasonable thing to expect of a car. A more reasonable thing to expect of a car is that the acceleration starts off really, really slow, but then amps up quite a bit, and then it'll eventually start to level off as you get higher and higher. But that's a more realistic graph. The green line is constant acceleration. And the red line is a more realistic graph. Okay. Notice it only had to hit 60 right at the 4 seconds and all that works fine. In fact, the problem is the slope right here would be instantaneous at, let's say, 1.3 seconds. The slope right here is tangent to it, and that's instantaneous at 3.0 seconds. So what we learned is x versus t, slope equals velocity, height equals displacement, and v bar equals slope between any 2 points, but v instantaneous is equal to dx over dt. And that means v bar is equal to delta x over delta t. And now if we do a v versus t, then what we find is the slope equals acceleration. I'll make that to a capital A. The height, and that means height of a data point, of course, equals velocity. And a bar, thank you, is equal to slope, which equals delta v over delta t between any 2 points. A instantaneous is equal to dv dt. Again, I go through the normal, limit process. That would be fine as well. I'll go ahead and write it this way since I was going to go ahead and skip it, but anyways. Like that. So we found out a lot of stuff, and this all should come in very handy. So for instance, we're going to start off, we started at 12, so we have until 120. Now I'm going to do something. I'm going to make use of what we found. Let's say if we assume the acceleration of an object is a constant, then we can set A equals a constant equals dv dt. Okay? So what I'm going to do is I'm going to say A. Actually, let's do it in a different color. And I don't necessarily, well, I'll do green. Is equal to dv dt. What I'm going to do with this is I'm going to multiply both sides by dt. So I'll get A dt is equal to dv dt. And now I'm going to integrate both sides without any range of integration. There's a way you can do it with a range of integration, but I'm going to do it without this time. And the left-hand side just becomes A times t plus a constant, which I'll call constant 1. In other words, since A is a constant, you're just doing the integral of dt, and the integral of dt is t. And of course, we didn't have a range of integration, so I have to add an integration constant. The right-hand side does something similar, except we use the fundamental theorem of calculus. Which says that the integral of a derivative is the original thing. So in this case, I'm just going to get v, I'm going to get v of t. And technically, well, I'll just call v at a particular time t plus a second constant, c2. Now from that, I can reach the conclusion that v of t is equal to at plus, I'm going to just call it a whole new constant, c. Remember, you can combine these constants all you want. Now, if we find if we are told the object had a velocity of v0 at t equals 0, then we can do the following. So at this time, what I'm going to say is a times 0 plus c is equal to v0, and that tells us that c is equal to v0. So we now have that v of t is equal to v0 plus at, or they usually don't write it in that function notation. We normally just write v is equal to v0 plus at. And that's one of the equations of kinematics. Sorry about that. Okay. Now that we have that, we can say, since v is equal to dx dt, we have v0 plus at is equal to dx over dt. I'm going to multiply both sides by dt again and then integrate. And what I'm going to get is the integral of v0 plus at dt is equal to the integral of dx over dt. So in this case, I'm going to get 1/2 at squared plus v0t plus c3 is equal to x of t plus c4. Okay? Which we can shorten to just say x of t is equal to 1/2 at squared plus V0t plus a whole new constant, C. If we are told that x is equal to x0 at t equals 0, then we get the following, which is x0 is equal to 1/2 a times 0 squared plus v0 times 0 plus c, which tells us c is equal to x0. And that gives us yet another version of a kinematic equation. Specifically, x is equal to 1/2 a t squared plus v0t plus x0. And both of these require constant acceleration. So this equation, this equation and this equation are only true for a equals a constant. Now that's pretty good, but what if we want to know a position or a velocity at some time later, but we don't have the time? Well, guess what? We can combine those two. So we can say V is equal to V0 plus AT, and we can use that to solve for T. That gives me T is equal to V minus V0 over A. And now I plug that in, X equals 1/2 A. This is supposed to be T squared, so I'm just going to put that squared plus V0 times V minus V0 over A plus X0. I'm going to pull the x0 over to the other side, get x minus x0, and then I'm going to get 1/2 of a, and then I'm going to have v squared minus 2v v0 plus v0 squared. All that's going to be divided by a squared. And then I'm going to distribute the v0 here, and I'm going to get v0 minus v0 squared over 2. I can continue again. And now I'm going to say, let's cancel out this A on the top with one of the A's on the bottom, and let's distribute that 2. And oops, I wrote 2 down there, and that's supposed to be an A. Sorry about that, everyone. I don't know why I wrote it. Yeah, that's supposed to be an A down there. So now what I'm going to do is I'm going to take v squared minus 2v v0 plus v0 squared, and all that's going to be over 2a because the a was already down there, as was the 2. And this one, I want to have a common denominator, so I'm going to go ahead and multiply through by 2 to get 2v v0 minus 2v0 squared, and all that divided by 2a. So ultimately, I get v squared minus 2v v0 plus v0 squared plus 2v v0 minus 2v0 squared, all that divided by 2a. You can see that this negative 2v0 cancels out with this one. And then ultimately, I'm just left with v squared minus v0 squared. Notice v0 squared minus 2v0 squared is just negative v0 squared, all that over 2a. So the way that we normally write this equation is v squared is equal to v0 squared plus 2a times x minus x0. And that is another kinematic equation that's supposed to be valid for a equals a constant. Okay. Now this whole process I went through is something you're supposed to be able to go through too. They will give you in practice tests and homeworks, they'll give you things like the acceleration's not a constant. They'll say like the acceleration is at, or the acceleration is 3t squared plus 4. And then you go through this exact same process integrating like I did there at the top of that page, and then like I did at the bottom of the page, but they have to give you those initial conditions. But in that sense, you need this technique that I went through as well as these results. By the way, in case I skip too many steps, I'm going to say x minus x0 is equal to v squared minus v0 squared over 2a. I can multiply both sides by 2a. That gives me 2a x minus x0 is equal to v squared minus v0 squared. And now I think you can see how I finally got that other form. So that is the kinematic equations you need to use, but they're all, remember, associated with sort of, other than this last one, are associated with a vector quantity. So if you draw your coordinate system, for instance, where the x-axis pointing to the right, if the object's moving to the right, then it has a positive velocity. If the object's moving to the left, then it has a negative velocity. If the object is speeding up going to the right, then that's a positive acceleration. If the object is speeding up going to the left, that's a negative acceleration. If the object is slowing down going to the right, that is a negative acceleration. And if the object is speeding up going to the left, that's a negative acceleration as well. So you got to keep that, or that's a positive acceleration. Sorry about that. No, that does work out to be negative. All of that sort of stuff you got to think about. Any questions on that? All right, so we now have our equations of kinematics, which is really what the rest of this chapter 2 is about. It's about you solving problems using these kinematic equations. I've basically covered up through section 2.4. So you should be able to do essentially half the homework by now. So, okay, Siri's trying to come on to me here and trying not to, they'll go away. No, thank you, Siri. Bye-bye. All right, so we have covered two dash one to 2-5. Okay, so that should give you plenty of stuff to start doing the homework with. I will solve a lot more problems next time, and I'll introduce the idea of falling objects and acceleration. So we're good now. It's now 1:20. Class is over. You guys are free to go. I'm going to wait for the last person to leave before I sign off. But I will see you all next week. And remember, we're assuming that I will be coming to class next week unless I send you guys an email. And that have to be out by 5 p.m. on Sunday. So if I send you an email saying I'm not going to come this week, I have to get that out to you by 5 p.m. on Sunday. So if you check your email, your TCC email on Sunday at 5 p.m. and you don't see anything from me, then you'll know we're supposed to meet for lab at 9 a.m. on Monday. Thanks for coming, everyone.
Wait, so clarify, you said that if we don't see something from you, then we're coming into class? Like
Exactly.
person in person? Okay.
Yeah, so I'm telling you right now, I'm planning on going actually to the building on Monday and starting to work in class. Thank you, Gabriel. Or Gabrielle. I got to figure that one out too.
Is our homework for this section going to be due? So it'll be due next Sunday?
It'll be due Sunday at 11:59. Yes, every Sunday at 11:59, you should have at least 2 homework assignments due.
Okay, so it will be due this Sunday. Okay.
Yes, ma'am.
And is the lab, I saw the email about the lab information,
Yes.
and I didn't know where to find it or if it
Okay, so you're in my 241 DO1B class. So you had lab on Monday morning at 9 a.m. I might actually be creating an actual Canvas page for our lab. It all depends because I do have some students that are coming from the night class, and if I have more than one, it's really a hassle unless I put them all. So there, I might actually open up the other Canvas page, and you'll be going there. But right now, all you do for lab is you just sign in with the lab Zoom message on Monday morning. And if you look in Canvas for this course, you'll see the one for lab as well as the Zoom meeting for lecture.
Okay, I meant the data that we need for the
Oh, gotcha.
um
Yeah,
like
I'm still having problems putting all that
okay.
together. So I pushed the due date back on that homework due to Monday. Just keep an eye out for your email. When I actually do post it, I'll post it. And obviously, since it's Monday, I don't have any time for you to ask me questions before then. So I'm gonna have to push it back from Monday anyways, just because I didn't get it done by today.
Okay, thank you so much.
You're welcome. I'll send an email explaining it all. Hopefully that'll help.
Okay, thank you. Have a good one.
You're welcome. You too.
Oh,
Anybody
I'm
else
just,
have any questions or anything?
yeah, I'm just clarifying. So the only assignments that were due so far were the chapter one conceptual and the chapter one just homework, the
Yes.
Pearson assignments.
Yeah, there was a couple of extra credits, but they're optional. And I can't remember what due dates I set for them. But if you actually get to them before I grade them, then I don't even take off for being late. So if you want to do the extra credits, just try to do them preferably by the due date because that's the
Yeah.
reason I gave it to you. But if not, just make sure you do it before I grade it and you'll still get credit.
So what are usually the due dates for? Okay, so I see for this chapter one extra credit, it's due on January 14th or the 16th. So those are
Right.
past due. But when are this extra credit due? The chapter two.
Uh, Let me see. I'm going to look at it real quick. I thought I already set any extra credits, but sorry, I got a stick in my throat. Huh. That's something going on with my throat now. Oh, okay. Yeah, I hadn't announced that one yet, so I'm just going to hide it until I figure out what to do with it. Sorry about that. Losing my voice now.
Okay. So we don't have any new homework except for the chapter two conceptual and the chapter two homework.
Exactly. Yep.
Okay. I was just wanting to clarify that. Thank you.
No problem. Thanks. Anybody else? That was Jordan, Guinevere, Megan. Anybody? See you,
Oh yeah.
June.
So about the extra credit, like how do I document it? Because I don't see you give like example of how the name of the file.
Okay.
I just do whatever.
You're going to upload it whenever you turn in any extra credit assignments, you're going to like do it on paper or whatever, take a photograph of it, save that as a PDF. I can give you some I can tell you about some apps I use for that if you want, but just find an app to convert photo to PDF, and then you just turn it in at the actual link where it only accepts PDF documents.
Oh, okay. Yeah. But the name of the file, like they are to be
Doesn't matter
classified.
because when you turn it in
Okay.
there, I'll already have your
Cool.
name on it. But when you're doing the actual labs, what I wanted was your first name and your first letter of your last name in the title for the lab. But even that, I'd still catch it. So it's just good practice to do that.
Oh, all right. Thank you. I got it.
No problem. Guinevere, do you have a question? Anybody else? I don't know if Guinevere is even there. I heard another voice when Tuan was talking, but I shall let you all go. Have a good one, everybody. Bye bye.